This is a brief lecture on digital clock and data recovery. Now we are familiar with the bang bang detector. We are familiar with the clock and data recovery based on the bang bang detector. What we have is a bang bang phase detector that determines the phase difference between the input data and the recovered clock. The outputs of the bang bang phase detector are up and down pulses which are given to a charge pump. Whose output is fed to a loop filter with a proportional output across the resistor R1 and an integral output across the resistor C1. And the control voltage so obtained, V control, is used to drive the VCO. This is the bang bang CDR with an analog loop filter. What we would like to do is to implement the loop filter entirely digitally, and the VCO will be replaced by a set of phases. VCO will be replaced by a set of clock phases which can be selected. Okay, so what we will look at now is a way to digitize the loop filter and the VCO and the function of the VCO. So let's look at what the bang bang phase detector does first. It looks at the phase difference between the clock and data inputs and gives outputs up and down, which are used to advance or retard the VCO. So let's say the data is like this: 1, 1, 0, 1, and so on. Okay. And let's say the clock is leading the data. That is, let's say that we would like to have when everything is settled, the falling edge of the clock should be coincident with data transitions, and this is how it should be. The falling edges should be coincident with data transitions. And let's say the clock is leading compared to what it should be. That is, it is something like this. As you can see, the transitions of the clock occur slightly before the transitions of the data. So the clock is leading the data. So in this case, what the bang bang phase detector does is to provide down pulses. That is, if the clock is leading the data, we would like to retard the clock so that it gets aligned with the data. So that means that the phase of the VCO should get retarded. That means that the control voltage should go down, or the down pulses should be, the phase detector should put out down pulses. So the up will be continuously 0 and the down pulses will be 1 for every time there is a data transition. So for this data transition, it's 1 here, and the next time there is no transition, so the phase detector output becomes 0, and for this particular transition again it becomes high, and for the next transition, that is this one, again it remains high. Okay, so this is up and this is down, and this is the case for clock leading data, and if the clock lags the data, let's say like this. In this case, I'll show the clock as lagging the data. You can see that the clock transition appears after the data transition. In this case, we would like to advance the VCO clock. So what happens is, in this case, the down pulse will be permanently 0, and the up pulses, you will get an up pulse for every transition that is lagging the data. So on. Okay. This is the clock, and this is the case for clock lagging data. So what happens is, whenever there is an up pulse, the control voltage of the VCO tends to increase. It advances the phase of the clock. Whenever there is a down pulse, the control voltage of the VCO tends to decrease and it retards the phase of the clock. The same effect we would like to do in a digital way without using an analog loop filter and an analog VCO. Okay. So to do that, let's first examine what happens to the output of the VCO in the analog loop, in the loop that we have. After that, we can see what happens. After that, we can see what to do digitally. I'll draw the charge pump and the analog loop filter here. So the charge pump gets inputs up and down. And the phase model of the VCO, of course, is the integrator. So if I want to just look at the output phase of the VCO, I'll use this model where the output is 5 VCO and K VCO is the gain of the VCO in hertz per volt. Okay. So now what happens? If there is an up pulse, let's say the up pulse is there is an up pulse for 1 clock period, then the voltage across the resistor VR will show a step which is like this, and the height of the step will be ICP times R, and the voltage across the capacitor C1 VC will increase from whatever value it has because of the up pulse, and the amount of increase can be easily calculated to be ICP times Tref, where Tref is the period of the up pulse, that is the charge, divided by C1. So now the voltage, the control voltage we control is the sum of the voltages across the resistor and the capacitor, and the phase of the VCO is the integral of the control voltage. Okay. The phase of the VCO is the integral of the control voltage. Now we have seen what happens to the resistor and capacitor voltages when there is an up pulse. When there is a down pulse, similar thing happens, except that the resistor will experience a step of minus ICPR, and the capacitor, the resistor voltage will do something like this, and the capacitor voltage will decrease by the same amount. Okay. So this value will be ICP Tref by C1. Okay. So if you look at the phase of the VCO after n clock cycles, it will be the integral from 0 to n Tref of the control voltage. And we also know that the control voltage gets incremented or decremented based on the up and down inputs. So the current input into the loop filter is ICP times up minus down, and the voltage across the loop filter will be the sum of the voltages across the resistor and that across the capacitor. So across the resistor you will have ICPR times up minus down, and across the capacitor there will be a voltage change which is equal to ICP Tref by C1 times up minus down. Now up minus down is up minus down can take on values of plus 1 if up is 1 and down is 0, 0 if both are 0, or minus 1 if up is 0 and down is 1. Okay. I will define a new variable Cp which is equal to up minus down, and this is a discrete time variable. This changes every clock cycle. Okay. So the voltage across the loop filter can be written as the value of Cp during the nth cycle times ICPR1 plus the sum of the values of Cp from 0 to n cycles times ICP Tref by C1. And the phase of the VCO is nothing but the integral of this quantity. I missed a constant 2 pi times KVCO here, that also needs to get multiplied. Okay. Now because inside the integral we have discrete time variables, the integral itself can be replaced by a summation, and phi VCO expressed as a discrete variable at the nth instant equals 2 pi k VCO times ICPR1 summation of Cp plus ICP Tref by C1 times the double summation of Cp. Okay. and this in turn can be written as okay. So this is an expression involving summations, and this can be realized using a discrete time circuit whose input is the discrete variable Cp, and Cp corresponds to up minus down. Okay. So if I write this in the block diagram form, Cp is up minus down, and the summation can be realized using an accumulator, and the double summation can be realized by accumulating the sum, and finally we have to multiply the summation by R1 C1 by Tref, add it to the double summation and multiply the entire result by 2 pi kVCO ACP Tref by C1. Okay, and what we will get will be a number that corresponds to the phase of the VCO. Okay. Now we are talking about implementing the entire thing in a discrete time digital fashion. So we have to approximate all these numbers by integers. Okay. So what we will do is we take up minus down, and up and down are simply single bit variables. So this means that the accumulator counts up. This is nothing but a counter that can count up and down. So if up is 1 and down is 0, it counts up. And if up is 0 and down is 1, it counts down. And finally, if up and down are both 0, the counter is frozen. Okay. So this can be implemented by a simple counter, and for the next stage we will need an accumulator. And this scaling is R1 T1 by R1 C1 by Tref, and we want to implement everything digitally. So what we do is we take the integer nearest to this and use that for multiplication. N1 is given by the integer closest to R1 C1 by Tref, and sum of these two is divided by N2. I said divided by because I know that the scaling factor here is going to be less than 1, and N2 is the integer that is closest to this number. Okay. So that is all that is there to it, and the output will be some integer which represents the phase. output will be some number that represents the phase. It is not necessarily an integer. So this is 5 out of n. Now to complete the digital implementation, what we do is, in this case we don't have a VCO. We don't apply this to the control voltage of the VCO. Instead, what we will have is a set of phases. So instead of the VCO, whose phase can be changed by its control voltage, we will have a fixed set of phases, okay, at the desired frequency. This is the clock, and let me call this phase 0. The phase 1 will be slightly phase shifted from this. And phase 2 will be even more phase shifted from this, and so on. And we can have a number of phases like this. Let's say we have a total of 32 phases. So then each of these phases will be separated by, a pair of these phases will be separated by 2 pi by 32, and phase number 31 will be something like this, okay. So if you go from m equal to 0 to 31, in each step you will phase shift by 2 pi by 32, and you go back from 31 to 0, you again phase shift by 2 pi by 32, okay. So as you cycle through these phases, you can select all of the phases, and if you cycle through them continuously, that is, you don't select one but you go on changing between them, you can also change the frequency, okay. So the output of the digital CDR is used to select the right phase, okay. So the possible phases, here the phase is quantized, okay. The possible output phases are two pi by 32. In general, if you have n phases, it can be 2 pi by n, okay, and it can have any value, m can have any value from 0 to 31, okay. So the output phase here cannot be arbitrary, it has to be one of these things. So what do we do? Phi out can equal any one of these, and this should be chosen from our digital loop filter. We have R1 C1 by Tref times single summation plus the double summation of the charge pump output. So we have to choose m, and this equality has to be considered carefully. It won't be exactly equal because the left side is quantized. We have to basically choose the nearest value, okay. So what we have to choose is m, the digit m, basically, which corresponds to which of the 32 phases we choose, and m will be given by n by 2 pi KVCO ICP Tref by C1 R1 C1 by Tref plus single summation plus the double summation of the charge pump output, okay. So which can be written as Okay. Now this entire number can be absorbed into another digit one by n3. So as it keeps accumulating, the right hand side of this keeps on changing. So as soon as it crosses 1, you make m equal to 1. As it crosses 2, you make m equals to 2, and so on. And finally, when it crosses 31, you have to wrap back to 0. So finally, the actual number will be this times this mod of 32, or in general, this mod n. Okay. So what we will have in a digital CDR is a phase selection block. We won't have a VCO. We'll have a number of phases available to us. We have to pick the digit m. We have to pick one of the phases, and that is given by the digit m. And m is given by this expression. Okay. So m is given by 1 by n3 something like this. And if we choose the numbers the way I described earlier, that is n1 equals r1c1 by tref and n3 equals 2 pi by n times C1 by 2 pi KVCO ICP Tref. This circuit will behave similar to the bang detector, the clock and data recovery circuit with the bang detector that you designed earlier. Okay, and to complete this, I also have to say modulo n. Okay, so this is the expression for selecting the phases. Now there are some implementation details. So let's say you have an analog clock and data recovery circuit with certain value of R1, C1, KVCO and so on. You compute N1, N3, they will come out to be some numbers. And then you put them here, you will get the value of M from this expression, and it is fine. But when you are doing all these digital computations, it will be very convenient if N1 and N3 are integer powers of 2, okay, or at least it is not a value like let's say 255 which has a number of ones. Then you can approximate this to 256 which has just 1 followed by 8 zeros. Okay, so that is a practical consideration. So for the assignment in the self-study course, you first compute the values that correspond to your analog clock and data recovery circuit and implement that. You take the nearest integers corresponding to these constants. Oh, by the way, these have to be the integers corresponding to these numbers. Okay, so you take the nearest integers and then you go one first step further and then approximate them by the nearest power of 2 and then see how the CDR behaves. Okay.